Okay, so welcome back. Today we are introducing you with another very important optimizer. And incidentally, today will be the concluding lecture on logistic regression model. So, welcome to lecture number 20. Okay, so basically, Newton's method is another optimizer. Sometimes it actually works much faster than gradient descent algorithm. Not sometimes, almost always. It is based on finding the local curvature of a function of several variables. I will take a digression from here because you need to have a concept of Hessian matrix to understand the Newton's method. So, it is basically concept of Hessian matrix. It is basically a square matrix of second order partial derivative of a scalar valued function or scalar field. Okay, so it actually physically describes the local curvature of a function of several variables. Okay, it is widely used in linear algebra for many applications. Okay. Let us try to see what it is. Say I have a function, it could be our likelihood function, LW, of several variables, right? You have W0, W1, W2, Wn, like that, okay? So, in that case, the Hessian matrix will be the partial derivative, second order partial derivative of this function with respect to all the variables. Say, here, look here, okay? So, this is a partial derivative of second order to the function of L with respect to parameter, so del W0 square, okay. Then del to L, del W0, so with respect to W0 you are differentiating the entire row, okay. If you have n number of n plus 1 number of parameters, so there will be n plus 1 number of column. This is the first row. So you understand that is del square L del W0 into del W2 like that, okay, up to del to L del W0 del Wn. Similarly, second row will be with respect to W1, so this is taking the first place, so del square L del W1 del W0, then del square L del W1 square, and so on and so forth, just like earlier. Okay, so what you are observing is the diagonal elements actually are del square L, del W0 square, del square L, del W1 square, del square L, del W2 square, etc., del square L, del Wn square. So that is a n plus n cross n plus n matrix. So this is called Hessian matrix. This Hessian matrix actually is doing this, okay. So this is an operator, del operator, del square, which is working on the function L, which itself is a function of several variables, okay. As simple as this, okay. Now let us see how we use it for designing an optimizer using Newton's method. Look carefully. This is, we have a cost function, say GW, it could be LW as well, okay. And say this is the function itself, okay. So if we could figure out for what value of W the function value becomes 0, then that value of W will be a solution to this function, okay. and you see the solution to this function. And how to figure out that is an iterative method. Perhaps you have studied it earlier in your numerical methods class. So let us see, there are points on the curvature. There is one point A, point B. So on point A, we have a tangent drawn, okay? And these are the parameters, okay? From here to up to this, okay? So this is W 0, okay? See, this is here to here, here to here. So this is W1, here to here, W2, so on and so forth, okay? So those are the parameters, okay? So it's clear, right? So say this is delta, this distance, okay? So by definition, that tangent at this point is the derivative, right? So J prime W0 equals to J W0 divided by delta, isn't it? That means this, what is this? This is nothing but for value W0, this is the functional value, that is JW0, okay? And by definition of derivative of this function JW, JW0 equals to the tangent at this point, okay? So this divided by this, okay? So this is already you know. From here, delta is equals to the functional value at W0 divided by derivative of that function at W0, okay? So we can write now iteratively, we need to run iteration, so we can write. So what will be the W1? W1 is actually, W1 is from here to here, okay? This is equals to from here to here minus delta. So W0 minus delta. So now we can just write down this equals to, so W1 equal to W0 minus, we are putting this delta value, this value of delta here, okay, which is clear, okay. Now in general form, so we have now the rhythm, okay. So W1 equal to W0 minus delta, okay. In general then Wt plus 1, so this is 1 more than 0, right. So T plus 1 equals to Wt, that is just like this. See this and try to understand, very simple. Okay, see this and try to understand this. Wt plus 1 equals to Wt minus J Wt divided by J prime Wt, okay. Now for optimizing any function, say Jw, we need to find W such that the J prime W will be equal to 0, okay. So then this is very interesting to note, that assuming Jw is J prime W, now same thing I can do. Suppose I am defining a function now. This is a J prime function, okay. This could be another function equals to J prime. So what this value will mean? This value will mean the optimum value of this function LW, right? Because now derivative of the function will have 0 at this point, right? So that's why I can replace the JW by J prime W, as I have discussed here, okay. And you can write down this Wt plus 1 equals to Wt minus j prime wt divided by j double prime, that means double derivative, okay, times wt. Exactly from here, if I just draw for you, I think it's clear enough, but still, okay. So now here is my j transpose, sorry, j prime w, and here is w, okay. So here is our w0, then say this is our w0, and this is the function, okay. So this is w0. Exactly, you do the same thing, but now this function itself is j prime w, and all others are same as here. And so what we are trying to figure out here, what is the value of w which will make j prime w equals to 0, okay. So if you can find that, then actually you are optimizing the actual function jw, isn't it? So that's the concept, and I believe you have got the concept, okay. Otherwise we can discuss in the discussion forum. Simple, okay. So I can now write down, okay, this, okay, and this is known as Newton's formula. Based on Newton's formula, I can update my parameter, okay. And this actually is turned out to be very, very fast, because it has Newton's method optimizer has quadratic convergence, okay. And quadratic convergence is very, very appreciable, because GDA has linear convergence. Quadratic convergence means, say in one iteration you could reach 0.01 of error. Next iteration, you can reach 0.01 square of the error, that means 0.001. Next, 0.001 square, that means 0.000000001 error, etc. So this is the meaning of quadratic convergence, which is, as you can observe, very, very fast. It will reduce error, okay. So in a generalized way, I can write down the formula which you have seen here, okay. This one like this, in terms of Hessian matrix, Wt plus 1 equals to Wt minus H inverse, that's operator, delta operator of Jw, where H is the Hessian matrix. As we have defined what Hessian matrix is, Hij equals to del square Jw divided by del Wi del Wj, okay. So this is a great optimizer, you can try. However, in machine learning, as you know that there is no free lunch. Here you will have to do, for each iteration you will have to make this calculation, that is, you will have to invert the Hessian matrix, okay. And if you have large number of features, then the dimension n is large, then inverting all the time, this is computationally intensive. And as you know, matrix inversion always require there will be no singularity. So if the singularity is there, then it may fail, okay. So that's the two disadvantage. Otherwise, it's great optimizer, and you should try, okay. Next, we are going to discuss about regularization and feature scaling of logistic regression model. Just like linear regression, here also you need to actually pre-process your data, like mean subtraction, etc., etc. Making mean 0 will be applicable here, okay. Also, you can do feature scaling, okay, like mean normalization, as you have done in linear regression. So this kind of techniques also need to be applied here, and you can also check as you did earlier, okay, whether your gradient descent algorithm is working well or not by plotting that cost function versus iteration or parameter, whatever it is. So it should be like this. It should be value of the cost function should come down iteration after iteration, then it is healthy. Okay. So these are these are good going. Okay. And here if you can see, sorry, these are not x, these are parameter W1, W2. So this is contour plot. If you see contour plot is almost circular, then that's a great thing. Okay. And when it will be circular, if you do the feature scaling properly. Okay. However, the bad thing is, so this is good, right? Okay. So these are good and these are bad. If your cost function iteration after iteration value is increasing, then it's bad, something is wrong. So you'll have to stop your algorithm and fix the problem. Or if you have elliptical contour plot, okay, so this is elliptical contour plot. So that is bad. It should be circular. Circular is good, elliptical is bad. So these are the things which you should remember, just like in case of linear regression, you remembered. Okay. There is also one issue with logistic regression model as well. Suppose you have two classes, okay, and the class and the samples are such that this is not a good fit, but you are biased, giving high bias, you made a very simple hypothesis or predictor, hx parameters by w is equals to the logistic function of w0 plus w1 x1 plus w2 x2, and you decided that, okay, I will not allow any more features, only two features. Okay, you have large number of samples, only two features you decided, that means you are giving high bias. Okay, so high bias, so underfitting will occur. So, and then this is an example of best fit, okay, and this is example of the extreme of the high bias. You decided that I will make high variance, okay. So you have less number of samples, for example, compared to features, and you have decided that your decision boundary should have separated everybody. So this is called overfitting problem, and both of them are bad because they will not generalize well. And when this can happen, when you have decided to design a predictor with very complicated, complex predictor, okay, a lot of terms are there, features are there, w0 x0 plus w1 x1 plus w2 x2, w3 x1, so all combinations. So this is another feature, x1 square x2, x1 square x2 square, like that. So you have decided that I will create large number of features, I will make my predictor complex, so that in the training, during learning, it should be able to separate clearly all the samples in the class. With that view, if you do that, then it is called overfitting problem. That is, it has high variance, low bias. And this is high bias, low variance, and both are bad. And this is incidentally is the best fit. That is, you have just incorporated the required number of features, okay, and it's neither very simple nor very complex. So in that case, you can get best fit predictor, which is desirable. Now you do not know, you cannot see that what is happening. So what this type of problem, how to avoid that problem? Okay, so this type of problem can be avoided. High bias problem can be avoided by making predictor more complex. right? So you whimsically put more parameters and more features, but at the same time you regularize. Okay, this is the concept similar to what you did in case of linear regression. So this is my cost function, and what I did, I used a regularizer term lambda divided by 2m. Why 2m? Because of mathematical convenience, as you know, summation of I equals to 1 to n wj square. So this term called regularizer term you have added, okay, and let us see what effect it has. As earlier, you know, if you run gradient descent algorithm, so this is how the parameters should be updated. W0 assigned to earlier W0 minus alpha by m. M is the number of sample, alpha is as usual learning rate. This is the derivative of the logistic regression cost function. Okay, so you know that. Okay, so this is right. So you know this logistic regression cost function. Because we are not regularizing normally the first parameter W0, which is attached with a fictitious feature x0, so we separately upgrade this parameter or convert this parameter. All parameters are like this: wj assigned equal to wj earlier minus alpha by m. So this is the derivative of the cost function. Okay, derivative of the cost function plus lambda times lambda j, but normally lambda is a constant, we keep lambda constant, so j will be same for all the features. Okay, so this is a lambda is a regularizing parameter. Okay, and j equals to 1, 2, 3, 4 up to n. N is the number of features. So this is the algorithm with regularizer, and as you can see, just like linear regression model, here also the parameter that is wj, okay, iteration after iteration is being shrinked with this value. Okay, so this value is much less than 1. Okay, because alpha is the learning rate, which is 0.01 say, and this is normally say 1000, 2000, whatever, and this is a large number of samples. Okay, 50,000 or whatever. Okay, so normally this is much less than 1. Okay, and so wj will be shrinking iteration after iteration, and then whatever whimsically parameter you have added, the model will actually self-correct by making many parameters vanishing, okay, or making them diminishing. So this is the regularization effect. Okay, this also you now learn. This is exactly similar to what you have observed in linear regression. Okay, so with this, I will also discuss some applications of linear regression model. This is widely used binary classifier. Okay, these are the following areas of application for classifying email, spam or ham, then for online transaction, whether it is fraudulent or not, then in business for assessing the chances that a customer will repurchase a product, respond to a direct mail or other marketing stimulus, whether she will respond or not. All kind of model you can just create using logistic regression and get benefit out of it. And in medical field also you have you can use it as a classifier. For example, a tumor, whether it is malignant or benign. Okay, and also there is a very important score called trauma and injury severity score, TISS, which was actually created by Boyd with others in 1987. which is a benchmark which is used for predicting the mortality for an injured patient. Okay, so logistic regression can help you to tell whether a patient who is injured will survive or not. Okay. As usual, there are some limitations also of logistic regression model. As you can see that logistic regression model is being linear classifier. It cannot be used for classes which are not linearly separable. If the training samples are less than or equal to the number of features, then logistic regression model may lead to overfitting problem. And logistic regression model may perform poorly if independent variables are not correlated to the target or are correlated to each other. So these are some of the limitations where logistic regression model may not function that well. Otherwise, it's a great classifier, and through this classifier you have learned many great concept of machine learning, that is specifically how to design intuitively a cost function, okay, and how to run a optimizer, how to improve optimizer, all kind of thing you learned during our lectures on logistic regression. Now we'll give you assignments. Come to the discussion forum if you have any problems, okay, and religiously solve those problems which will be given to you exclusively on logistic regression. Okay. Hope you enjoyed these videos. If you have any problem, you come to the discussion forum, and stay safe. I wish you all the best. Bye bye.